So everybody's just about turned in the homework. I'm going to start by just going through this problem that we have, and dry erase marker is not going to work on a chalkboard. So this was another example of a system that's equivalent to saying that you have resistors in series. So for this problem, I tell you that you have these two spherical shells, where the first one has some constant resistivity of rho 1, and the second one has some resistivity, rho as a function of r is equal to rho 0 times r divided by c, where this is some radius of A, this is some radius of B, this is some radius of C. And you want to find what the resistance of the system is, or you want to find the current that flows through the system if I connect this to a battery with some voltage of V. Okay. So in order to do this, I'm actually going to show you two ways. I've been kind of holding out a shortcut on you guys because I wanted you to go through the full calculation before we learn the shortcut. So we'll do that first, and then I'll show you what the shortcut is. But ultimately what we want to do here is we want to find what the resistance of the system is, because we know that the difference in electric potential is going to be related to the current times the resistance, and we know what the voltages across these, and if we find the resistance, we can find the current. Okay. So the first thing that we can do is write down the microscopic form of Ohm's law. This is just E is equal to rho J, and then realize that we have two different regions that we need to consider here. So for both of them, actually, we can say that I is equal to the integral of J dot dA, where here this is going to be reduced to J times A, which, because these are spherical shells, the area that you're interested in here is just going to be 4 pi r squared. Okay, so this says then that J is going to be equal to, this is going to be rho I divided by 4 pi r squared. Okay. So then what we want to do is we want to consider the fact that we have different resistivities in these two regions. And so what that says then is that E vector 1 is going to be equal to rho 1 I divided by 4 pi r squared times r hat. And then E vector 2 is going to be equal to this function that we have. So this is rho 0 r divided by c divided by 4 pi r squared times r hat. Okay. Now the last thing that we need to do here is to find what the difference in electric potential is, and that's just to say that delta V, the difference in electric potential from A to C, is going to be equal to the negative integral from A to C of this is going to be E vector dot dl. But then we realize that because we have two different electric fields here, we need to break this integral up into two pieces, and so that's to say that this is equal to the negative integral from A to B of E1 dot dl minus the integral from B to C of E2 dot dl. Okay? So now what we can do is we can plug in our electric fields, and note that dl in this case is going to be equal to r hat dr. Why is this going to be r hat dr? Because it's more specific. It has to do with that. It has to do with that. It's in polar coordinates, and what we're doing when and the real meaning of this integral when I'm finding this difference in electric potential is I consider what the electric field is, and then I want to walk from A to this is the lower limit of the other one. That's why that looks weird. I want to walk from A to C, right? So to go from A to C, and what I'm doing is I'm adding up all of the electric field as I'm making this walk. This walk that I'm doing is in the radial direction because it's spherical. Okay. What's that? Yeah, sorry, I left that off. Yeah, this has an I here. Okay. So now that we have our general integrals set up here, we have our electric fields, we can plug those in and evaluate these integrals. And so this says that this is equal to the negative integral from A to B of rho 1 I divided by 4 pi r squared r hat dot r hat dr minus the integral from b to c of rho 0 r divided by c divided by 4 pi r squared I r hat. Dot r hat dr. Okay, so when we go to evaluate this, we see that dot products are all 1, which is nice. Everything here except for the r squared in the denominator is a constant, and so we can pull that out, and so this is going to be equal to minus rho 1 I divided by 4 pi. The integral of 1 over r squared dr is going to be negative 1 over r, evaluated from a to b. And then this one is going to be minus, I have an r here that's going to cancel with the r in the denominator. This is going to give me a natural log, and so this is going to be rho 0 I divided by 4 pi times the natural log of r evaluated from b to c. Okay?
What happened to the c? It was rho naught times r over c.
That should be here too, sorry. Yep, that's there. Not a good day for me carrying all my constants through. Okay, so now what we can do is we can evaluate these limits, and what we end up seeing is that this is going to be equal to, in order for this to be positive, because ultimately we want the magnitude of delta V, we're going to take an absolute value here. And so that's going to give me a rho 1 I over 4 pi times 1 over A minus 1 over B. Plus rho 0, and let me factor out the i's here. So plus rho 0 divided by 4 pi c times the natural log of c over b times, now the whole thing is going to be multiplied by I.
Would it be 1 over b minus 1 over a?
1 over b. So when I took the absolute value here, that reversed this. And that was, because you're right, for the way that it's evaluated right here, this would be 1 over b minus 1 over a, but I want this to be a positive quantity. And because a is less than b, 1 over a minus 1 over b is positive. So I reversed it in that step. But you're right, just going from this line to this line, that would be 1 over b minus 1 over a. Yeah?
So when you take the absolute value, you're making everything positive? Like, are you allowed to do that? Because wouldn't some of the things like cancel out with each other and then become positive? That's like what I'm getting hung up.
Well, anything that would cancel would still cancel if you took the absolute value of the whole thing. But it's not absolute value term by term, if that's what you mean.
Yeah,
it's absolute value of the entire thing. So I think what's bothering you is, why is there a minus b here, maybe?
I think he didn't catch the negative in the 1 over r.
Okay, well let me do the whole thing then. So this is going to be rho 1 I over 4 pi. This just becomes positive, right? Because it's negative times 1 over b minus 1 over a, right? When I evaluate this exactly the way it is. And then what I did was I reversed these two, because I know that A is less than B. And so let's plug some numbers in here to see why it is that I would want to reverse this in order to make it positive in the end. Let's say that B is 5 and A is 2. So if I do 1 over 5 minus 1 over 2, this a fifth is smaller than a half, right? So this would give me something negative, which is why when I wrote it here, I reversed them. So I have 1 over a minus 1 over b.
I understand that, but why? You have two values in the absolute value, right? Like in your.
Yeah. I have this and I have this.
Yeah. So if one of them turned out to be positive and one turned out to be negative, then like part of them would cancel out with each other, and then you take the absolute value.
Well, really, yeah. I guess I see what you're saying. It's not really the absolute value of the whole thing. It's the absolute value of each individual one, because really what I'm doing is I'm saying it's the absolute value of the V total is equal to the absolute value of V1 plus the absolute value of V2. Okay. Yeah. Okay. It's better. Okay. Any other questions? Yeah.
So in general, it's not allowed to combine resistances, because I did a problem by finding the resistance of each shell.
Yeah, no, you can absolutely do that, and that's actually where I'm going with this, because you see that these are just resistors in series, and so you could say that the equivalent resistance is just going to be equal to R1 plus R2, and calculate these individually and add them together. It gives you the same answer. But what I'm trying to do with these kinds of problems is I'm trying not to use this, so that you can see where this equation comes from. And then for problems on the test or working the old exams, it's perfectly fine to use this. It's true. It's true that this is true. And actually, I don't know if I explicitly made you do this. Yeah, I didn't explicitly tell you had to do it this way, so it was perfectly fine to do it like this. Okay. Yeah.
There's a row in where J is calculated up there, and I don't know.
Yeah, so it's row and not row 1 or row 0.
Well, like, so if I is equal to J times the area.
Oh, that's a mistake. That should be E. If I wrote it like that, that should be E. This should just be. Yeah. And today was not a good day for the constants. Okay. Other questions? Okay. So now that I have this, I know what my difference in electric potential is. I know that's just going to be V, and so in order to solve for I can just divide V by this, okay? But as you were saying, when you look at this, actually, this is identically R1, and this is identically R2. I can just calculate those two things explicitly, and then just add them together, because these are in series, right? I can add them together like this. And so I don't really have to go through this whole process the way that I did here. And there's actually another shortcut. I talked to some of you guys about this yesterday, and again, the reason why I'm doing it the way that I am right now is because I wanted you to see where this came from. If I want to find some total resistance, I can say that the total resistance R is just going to be equal to the integral of dr, right? I just add up all of the little pieces of the resistance to get the total resistance. And this dr here can be parameterized such that dr is going to be equal to rho dl divided by A, where this dl is the same dl that I would have here. It's a scalar, not a vector, but it's still the same direction, so for this case it would be dr. And A is going to be the area that the current density flows through. So in this case, if I say that A is going to be equal to 4 pi r squared, and dl is just going to be dr, and rho is whatever rho is for each individual region, I can just calculate it explicitly like this, and I don't have to go through the whole process of using the microscopic form of Ohm's law. Okay. But like I said, I wanted you to go through this whole process here to show that really what we're doing is, and it's the same thing that we did with capacitance, it's getting our electric field to talk to an electric potential in a way that we can write the resistance in terms of the electric potential. In the case of capacitance, it was to write the capacitance in terms of the electric potential, and that was getting the electric field to talk to the electric potential. Okay. So any questions about this? Okay. So for today, what we're going to do, and this looks kind of long, it's not as long as it looks, because I just explicitly wrote out all the steps. Today, what we're going to do is we're going to talk about how we can go through the same process with resistors in parallel. So up until now, we've just done resistors in series, but we want to talk about how we can do this with resistors in parallel. And ultimately, what that comes down to, in order to get this equation where we said that REQ is equal to R1 plus R2, we said that the current is going to be the same in these, so I1 is equal to I2 is equal to I total, and the difference in electric potentials are going to add, so delta V1 plus delta V2 is equal to delta V total. And then from this, what we were able to do is we were able to show that this relationship REQ is equal to R1 plus R2. Our goal with doing this with resistors in parallel is to do something similar to this, only now instead of saying that the currents are the same and the difference in electric potential adds, so this is for series. In parallel, we say that the currents add, so I total is equal to I1, so much for that piece of chalk, I1 plus I2, and delta V total is equal to delta V1 plus delta V, is equal to delta V1 is equal to delta V2. Okay, so you can see the comparison between these, and ultimately, again, I don't want you to just use this equation. I want you to go through the process of showing why it's true. Ultimately, that says that for resistors in parallel, they're going to add like this. Okay, so go ahead and get started on that, and I'll come around and answer questions as you guys have them.